All right, thanks a lot. Yeah, I mean, thanks a lot to the organizers for inviting me here today. Happy to talk a bit about linear models. I really try to kind of like do this more like a lecture to kind of try to provide some background and hopefully helpful tips. So unfortunately, I don't have as many awesome papers to show as Carson just did. But yeah, nevertheless, hopefully helpful. So the way that we got into kind of like realizing the need for linear models as an approach to kind of like analyze neural data, in our case, came from imaging, where we particularly like to use wide field imaging, which is this macroscopic approach to look at cortex-wide activity. So in this case, we have a head-fixed mouse, and we can at the same time look at its cortical surface. And this is imaging through the intact skull. So this is a transgenic animal where we look at calcium dynamics with an indicator. And we can overlay this with an atlas to realize that we basically have this access to all these different cortical areas, and then just measure changes in fluorescence as our functional signal. And when we looked at these cortical dynamics, we can see that many of the activity patterns are tightly linked to the ongoing behavior of the animal. So you can see the animal is doing this behavioral task, and every time it's doing something in particular, you see all these cortex-wide activity patterns. And unfortunately, not everything the animal's doing is necessarily what we asked it to do, right? So for example, when it's licking its paws, that drives a bunch of very defined activity patterns. And clearly every area is doing more than one thing, right? So all these behaviors kind of coalesce into this very complicated mixed signal. And when we looked at the activity and we aligned it to the task, so this is basically pictures of trial averages for different periods of a task, and then looked at the activity, in this case, for example, in the auditory cortex, or in this case, in the frontal cortex, it's kind of apparent that it's tricky to interpret these trial average data by itself. For example, in this case, this is the onset of a stimulus here in this gray box, and maybe we see this uptick in activity in this green trace. And so we could say maybe that's the stimulus response, or we see this ramping activity in the frontal cortex, and we could say maybe that's the decision-related activity that we see. But overall, you can tell that there's many different things going on, and we wondered if there's a way to separate the features that drive these differences in neural activity. So can we somehow unmix them? And the answer to that is yes. So we can use these linear encoding models to try to isolate different features that drive neural activity and then split them out so that we can look at the responses to these different features in isolation. So in this case, these examples show the cortical activity in response to the animal touching a handle, for example. So here it's using its right paw, and we get this very defined activity in the left somatosensory motor region. And then on this other example, you can see the response to visual stimulus, which again is very defined in the left visual cortex. And what's nice about these linear models is that you can apply them to many different types of data. So like this is not limited to imaging or any other kind of neural measure. So we also use this on Neuropixels recordings, where the only confound is basically that you also have to use a binning or some kind of smoothing in order to get to a signal that is a bit more continuous, and you can look at changes in firing rates rather than individual spikes. There are more sophisticated ways of really looking at like binary events, but I'm not going to talk about that today. So in this example, I just wanted to mention that basically in this case, when we look at neural responses from Neuropixels, we could use the linear encoding model to kind of split out the responses that are driven either by a stimulus or by the movements. In that specific example, we found that this neuron was really driven by the stimulus and not potentially by a correlated movement that could have co-occurred with the stimulus. Okay, but how do we get to doing that kind of splitting into different features? And when you think of the neural responses, like in a trial average, for example, you could do a PSTH of a neuron, and you can look at its response to a stimulus. And you can see here that if you average the activity in response to the stimulus, you would see this clear increase. But we can also look at this a little bit differently in the sense of a correlation, where if we would have modulated the intensity of the stimulus and looked at the changes in neural activity, we could find that as we increased the intensity of the stimulus, we would also see an increase in neural activity. And then we could describe this as a correlation. So we could basically build a prediction of how the stimulus is driving the neural response. So like just the very simple linear regression. And when you think of how that works, is basically you have your prediction of the neural data y hat, which is explained by your stimulus x given some weight, which would be the regression the regression coefficient of this line, so just the slope of this line, plus some offset term that defines on where you start on the y-axis. So it's like a super simple starting point. And what's nice about regression is that the same rule applies when you increase the number of regressors that you're using to predict the neural data. So this is now multivariate linear regression, where instead of just using a single regressor to predict your neural data, you can basically just add terms. So basically you can have your weight 1 on your x1, but you can basically keep adding that up until you have your weight r on your stimulus or whatever feature it is r. And all of those summed together then basically make your prediction y hat. So in that case, basically you can combine as many features as you like and try to explain the neural data. And you can then look at the weights of these different features to have an indication of how important every feature is to actually explain the neural data itself. And one thing that's helpful here is to do z-scoring or some kind of normalization on the different regressors that you're using. So that's the weight is actually informative, because if you're using measures that have different units, obviously the weight will rescale depending on the unit of measure. And that's not very helpful. So then you can combine all these different regressors. So just as an example here, so for example, you have some information from point tracking data and you can put these together, and then you get the weights from the model, and then you have your prediction of the neural data. So this could be the activity of individual neurons. And then here the beta weights would be indicative of the relative contribution. However, when you think of the stimulus response as a binary event, there's a bit of an issue, and that is that they're not continuous variables. Like basically they're more like an impulse, and you want to know how the neural responses follow that stimulus forward in time. But the neural response is usually unknown and somewhat complicated. So there is a question if you can use this approach to also predict a response, like, not just an instantaneous measure, but some response to a binary event. And you can do that by taking a binary regressor and then just shifting it in time. So basically here you have a single binary regressor. So this would be whisking events. And you can then make copies of this regressor and shift them forward and backward in time. And what's cool about this is that because they're 0 everywhere but at the time of the occurrence of that event, the weight that this regressor will take is the best way to explain the neural data at that specific point in time. So when you take that regressor and you shift it forward in time by one sample, you now get another weight for that other regressor that is predictive of the neural activity at this other point in time. Right. So basically by creating this matrix of regressors, so this is called the design matrix, you can basically get a set of weights for each of these regressors. And when you put them together, you can basically get what's called a response kernel, which is basically the neural response to that event, but not just at that moment in time, but also earlier or later, depending on how you're shifting these regressors around. And in this example from the imaging data, you can see, for example, for these different cortical areas, this is the response to the whisking, where like this region responded a bit earlier in time and this other one responded a bit later. And you can basically describe these response features really well. And a way to think about these response kernels is basically that they're like feature-specific trial averages, like a PSDH. But basically, if you pull them out of a larger model that can account for different factors, this PSDH is basically the one that is the response to that specific feature, whereas the response to other features lives somewhere else in the model. And if you sum them all together, you would get the full neural prediction. Okay, and the other thing that's interesting about how to build these linear models is that you can combine both analog as well as binary regressors in the same model. So a binary regressor would be something like this, like, it's either 1 or 0, and you can build these design matrices from it. But an analog regressor would be what I showed earlier for normal regression, where it's basically just a continuous regressor that you can correlate against your data. You can shift it around in time as well, but basically the weight of it is just how strongly you can rescale it to match the neural data directly. And just as an example, so this is a recent paper from Ode Lewis et al., who were using a model like this, where they have both binary as well as analog regressors combined in a larger model to predict neural responses in visual cortex, both to visual or auditory stimulation, and showed that the trial average response that you see in that case is indeed a combination of true sensory responses and a movement component in different parts of the cortex. Okay, so as I mentioned, you can basically try to assign by kind of like using these different weights, the contribution of how different regressors are shaping neural responses. And the beta weights are important here. But one thing that you can also use in addition is the R-square value, which is the coefficient of determination. So it's basically just saying how much variance your model can explain in the neural data. And the reason why that's important is because when you look at a trial average, you basically see the averaged activity over all your trials, but you don't really know how the individual trials look like or what else is going on when you think of spontaneous data. And the R-square, in contrast to that, is basically just saying, if you think of your full model, how much of the overall variance in your data can be accounted for by using that model. And in this example, for example, when we looked at this null response in the Neuropixels recording, although the stimulus response was actually well predicted by stimulus regressors, we actually found that the movement regressors were the ones that explained most of the variance. It just happened that in this case, the movement was not aligned to the stimulus onset. It was just ongoing activity. So in that case, if you average over all your trials, that is kind of averaged away and you don't really see it on average. So whether or not the trial average and the R-square go together depends a lot on whether what's driving most of your variance is also related to what you would see on a trial average. That's not necessarily the case. And when you compute the R-square, you can also use it to just evaluate how well your model can predict the neural data at all. Like if that's low, maybe you know that your model isn't super great. But you can also use it to quantify the ability of individual regressors in your model to explain the neural data. So for example, you can take the full model, or you can take individual variables, or you can also use groups of variables and ask how well they are predicting the neural data. So in that case, you can see here when we compare the predictiveness of a full model versus a model that is only using movements, they're very similar, whereas the stimulus only explains the neural data for some neurons, but not for others. And we can take advantage of that to quantify how well individual variables really contribute to explained variance. And what's neat about this is that you can kind of think of it as a sum of a big whole. So when you look at these two circles, that would be a representation of the explained variance. And in this case, both of these circles combined would be how much a full model can explain the variance in the neural data. So that would be the explained variance. However, if I take a feature out of the model, some of the explained variance is now lost. So basically removing some features that are informative from the model makes the model worse. But at the same time, when I add that feature back in, not all of its explained variance is visible in the model because some of the model components might be redundant. So in that case, there's a certain amount of shared explained variance that the model can compensate for if I remove a variable. But at the same time, there's some unique explained variance that you can really only account for if that regressor set is added. So you can quantify both the explained variance in total, but also how much of that is shared and how much of it is unique to some specific set of variables to really account for if they are important to explain the neural data. So in that case, that would be the difference between the full model, which is the combination of the green and the blue, versus a reduced model, in that case, only the green. And what's remaining here would be the unique explained variance of that feature. Okay, so then another thing I wanted to mention is the problem of model overfitting. So when you build a lot, oh God, I'm really low on time, dang. So I'm going to speed up a little bit. So overfitting is really important when you build these models, because when you add regressors, the model will always become better. So when you add kind of like a lot of kind of random variables to your model and you just do a model fit, you will find that your R-square during fitting can still increase. And that's because you just give the model more flexibility to match the neural data. And so in the extreme case, if you have as many regressors as you have data points, you could predict anything, but that is not really helpful. So a nice model fit in the fit itself doesn't mean that it would be a meaningful, model. So in order to get there, you have to translate it to unseen data, as has been mentioned earlier. And only if you can see that the R-square is high when you test it on some test data that wasn't part of the fitting, you can hope that the model is actually informative. And as a rule of thumb, to avoid overfitting, you don't want to have more regressors as about 10% of the data points in your recording. With Neuropixels, that's usually not a problem, but it's very important to be aware of the issue of large models at large. So in this case, I'm just going to mention that, one way to get around this issue is cross-validation. You always have to think of cross-validation or some other way of using test data to validate these models. And only when you see good performance in your test, you can really think that your model is informative at all. The other point I wanted to mention is regularization. You need to often regularize these models because if you have regressors that are related to each other, you have a model that has multi-collinearity in it, meaning that some regressors can explain the impact of other regressors, which means that you have different solutions to basically describe the neural data, which leads to unstable weights. And the way to go through that, I'm not going to comment on this anymore. The way to go through this is that you have to apply some kind of regularization. There's different ways of doing that. So you can do lasso, ridge, or elastic net regularization. And the one thing to know is that if you use lasso, which is also called L1 regularization, you will favor a model with sparse weights. So many weights will basically just go to 0, and only the really good ones will remain. Whereas ridge, you will favor a distribution of the weights across many regressors. So this is a model that would favor combining many regressors if you want to avoid that single features dominates the performance of your model. And elastic net is a compromise between the two. Okay, so just to summarize, you can use linear models to unmix neural responses into different features. You can use these models as a combination of analog or binary regressors to achieve better fits and interpret the neural responses. And the model weights can reveal feature importance and also how the neural responses might look like. Then the explained variance is very informative, and you can kind of go into the shared or unique variance to be more informative. It's important to know that unique explained variance is very conservative, because anything in the model that could account for explained variance, you will not see. You really only get what that is, the information that is truly unique to a given regressor. Regularization important, cross-validation very important, and yes, that's kind of what I wanted to say. If you want to get started on using these codes, we have a repository of MATLAB code to build linear models the way I just explained. It's meant for wide field data, but it also has examples for Neuropixels, so you can look at these codes to see how we use them. The key function in that repository is called Ridge MML, which is a ridge regression model that Matt Kaufman built that works really well. It's very fast. But there's also Python implementations like the one from Michael Sokoletsky, and also the NEMOS project from the Flatiron, which has a lot of very sophisticated modeling code.